All right, section 4.4, multiplication rules, the basics. What we're going to be doing here is looking at a multiplication rule and how it's used for finding the probability of both A and B occurring at the same time. Last time we looked at the probability of A or B, so this is now the intersection, as long as the two events are independent. It says if the outcome of the first event A somehow affects the probability of the second event B, it's important to adjust the probability of B to reflect the occurrence of event A, and we're going to look at how to do that. The probability of event A and B is equal to the probability of event A occurring in a first trial and event B occurring in the second trial. This could be written as the probability of A intersect B. If we have a conditional probability where we have this vertical line right here, this is read the probability of B given A. Let me write that out in words. The probability of B given A means we want to find the probability of B given the condition that event A has already occurred. And if A and B are independent, then the fact that A has occurred isn't going to affect the probability of B. But if they're dependent, knowing that A has occurred will affect the probability of B. So I don't want to tell you what it means. I want to tell you how to interpret these symbols in your mind. When you see these symbols here, you should be thinking the probability of B given the condition that A has already occurred. The intuitive multiplication rule says that when finding the probability that event A occurs in one trial and event B occurs in the next trial, then we would multiply the probability of event A by the probability of event B. But we have to do so in such a way that the probability of event B takes into account the previous occurrence of event A. That gives us this rule right here for multiplication. This is the formal multiplication rule. The probability of A and B is equal to the probability of A times the probability of B given A. Now, when applying the multiplication rule, you always want to consider whether the events are independent or dependent, and then adjust the calculations accordingly. If these events are independent, the fact that A has occurred isn't going to change the probability of B, because the probability of me being late to class, given that the stock market is up 3 points. Those two things are independent. The probability of me being late to class is the same regardless of what the stock market does. Even if it crashes, I'm still going to be at class, although I might be running late. They would be independent. So this given condition then would not affect the probability of B. So what we would say then is if A and B are independent of each other, then the probability of A and B is going to be equal to the probability of A times the probability of B. Here's a couple problems out of your book. The instructions precede the questions. So for questions 5 through 12, we're asked to A, determine whether events A and B are independent or dependent, and then B, find the probability of A and B, the probability that events A and B both occur. Event A in number 6 is when a baby is born, it is a girl. Event B is when a second baby is born into a different family, it is also a girl. Does the birth of one child influence the sex of one child, influence the sex of another child? No. So these two events, we would say, are independent of each other. And because they are independent, then we could say that the probability of event A and the probability of event B would be equal to the probability of event A times the probability of event B. What is the probability that a baby being born would be a girl as opposed to a boy? The probability of A is the number of ways we can come up with event A divided by the number of elements in our sample space. Same thing for the probability of B. Event A here is that you have a baby girl. How many ways can you have a baby girl? One way. Out of what are your choices or your sample space? 2, a boy or a girl. So this is going to be equal to 1/2 times 1/2 or 1/4. The probability of A and B both occurring is 0.25. Number 8, when a day of the week is randomly selected, it is a Saturday. That's event A. Event B is when a second different day of the week is randomly selected, it is a Monday. So here's event A and here's event B. Does the probability of one affect the probability of the other? These two events are actually dependent because the probability of randomly selecting a day of the week, there's 7 days in a week, the probability of event A would be 1/7, having that day be a Monday. When we have to select a different day, the fact that we've selected Monday for the first event now changes our sample space to not include Monday, because we have to select a different day. There's 6 different days that we could use then for this. These are dependent events because knowing that we've selected one day has changed the sample space for the second event. So we would use the formula then. The probability of A and B will be equal to the probability of A times the probability of B, given that A has already occurred. All right, we can do this using common sense and without using a formula. The probability of A is the number of ways that we can come up with A divided by the number of elements in our sample space. Here the probability of B given A is going to be the number of ways we can come up with our event B now divided by the number of elements in our sample space, given that A has already occurred. How many ways can we come up with a Saturday? Just one. Out of how many days in the week? 7. On part B, we have to select a different day of the week, and that different day of the week is going to be a Monday. There's only one way we can come up with a Monday, but now out of how many days do we have to choose from? 6. So this probability would be what? 1 out of 42. Do you see why these events are dependent? Once I selected the first day, I selected event A. Event B has to be a different day. So I've removed one of the choices from the sample space, so that's ended up changing this value right here, the number of elements in the sample space. The multiplication rule for several events. In general, the probability of any sequence of independent events is simply the product of their corresponding probabilities. Let's see if we can do this example now. It says a junk box in your room contains a dozen old batteries, 5 of which are totally dead. You start picking batteries one at a time and testing them. Find the probability for each of the outcomes. So how many batteries do you have in your drawer? So the number of elements in our sample space is 12. We have 5 bad batteries and 7 good. In part A, the probability that the first 2 you choose are both good. So here our event is that we're choosing a battery that's good. And the way I think about these is I've got 2 operations here. I'm choosing one battery first and it's good. And then I'm choosing a second battery and it's good. The probability that the first battery is good is going to be 7 out of 12. The second battery now also has to be good. So how many good batteries are left in the drawer? 6 out of 11. So this probability then would be 7/12 times 6/11, 7 out of 22. We have this decimal when we convert it to a fraction, it's going to give us 7/22. Math enter converts the decimals to the fractions. B, it says at least one of the first 3 works. So at least one of the first 3 batteries you pick is going to be good. Do you remember me talking last time about the dangers of at least one? This is where it's easier actually to find the probability of the complement. So on part B here, our event is at least one good. And we want to find the probability of our event. But in this case, it might be easier to find the probability of the complement. So E complement would be none of the batteries are good. The complement of at least one is none. And the reason I want to find the complement is if I tried to just head on find the probability that at least one is good, I would have to find the probability that the first one's good and the second 2 are bad. The probability that the first one's bad and the second one's good and then the third one's bad. I'd have to add up all of those different probabilities. If I tried to do this head on, I would be looking at good, bad, 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 good, bad, 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 good, bad, good, good, because 2 good is at least 1, isn't it? And then I'd have to find good, bad, good, 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 bad, and then all 3 of them could be good as well, right? it's easier to find the probability that none of them are good. There's only one way that can happen. So instead of finding all these probabilities and adding them up, and this is not our sample space. Our sample space, remember, is the 12 batteries. I would have to do all this, and I'm not going to do that. Let me erase this, and we're going to recall that the probability of our event E will be equal to 1 minus the probability of the complement of the event. And there's only one way that all 3 batteries would be bad. So we look at this and decide that the probability that all 3 batteries are bad would mean that the first battery is bad, and the probability of that happening is 5 out of how many? 12. There's 12 batteries in the drawer. The second one's bad as well. So now how many bad batteries do I have to choose from? 4 out of 11, and then 3 out of 10. So this probability is easier to calculate because I don't have to find all of the other probabilities and then add them together. So I need to multiply this out, 1/22. So there's the probability of the complement of the event. How do I now find the probability of the event? It's 1 minus the probability of the complement, which is 1/22, and that's going to be 21/22. Well, that means that out of 3 batteries, just reaching in and grabbing 3 batteries out of the drawer, the probability is pretty good that at least one of them is good. Seems reasonable. Part C then, the first 4 that you pick all work. Find the probability that the first 4 that you pick all work. So I'm picking 4 batteries. There's the first battery, second, third, and fourth battery. Probability that the first battery is good is 7 out of 12. Then I have 6 out of, 5 out of, and 4 out of 9. So we can multiply all this out and we would get, find the probability that you have to pick 5 batteries in order to find one that works. What does that mean? What do we know about the first battery? Did it work? Second battery? Third battery? Fourth battery? Fifth battery? It worked. So what's the probability of the first battery not working? 5 out of 12. Remember, there's 5 bad batteries, 7 good batteries. What's the probability the second battery didn't work? 4 out of 11. Third battery doesn't work. Next battery doesn't work. And then the next battery does work. What's the probability that that battery works? You've selected all those batteries out of the drawer. There's 12 batteries total, right? So once we took the first battery out, we were down to 11, and then 10, 9, 8, 7. Our sample space is decreasing by 1 each time because we're removing a battery. Remember, the sample space is all the batteries in the drawer. So now we need to multiply this out. All right, dependent and independent. 2 events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. We've already had that discussion. For example, me being late to class and the stock market going up or down. They don't affect each other. So several events are similarly independent if the occurrence of any does not affect the probabilities of the occurrences of the others. The last example that we did, everything was dependent because once we selected a battery, then our sample space was changed, and the probability of then drawing the next battery being good or bad, that depended on the first battery that we drew. So those were dependent. If A and B are not independent, then they're said to be dependent. 2 events are dependent if the occurrence of one of them affects the probability of the occurrence of the other, but this does not necessarily mean that one of the events is the cause of the other. 2 events can be independent without the causation. Just because I drew a bad battery first, that didn't cause me to draw a good battery next. Here's an example problem. It says real estate ads suggest that 59% of homes for sale have garages, 30% have swimming pools, and 2% have both features. What is the probability that a home for sale has a pool or a garage? We're reviewing a little bit here. Or means what? Union or intersection? Union. So what we're looking for here in part A is the probability that the home has a pool or a garage. Well, remember the addition rule? That's going to be equal to the probability that the home has a pool plus the probability that the home has a garage minus the probability that the home has a pool and a garage. If there's overlap, you counted it once with the pool, once with the garage. It got counted twice, so take it away once. The probability that a home has a pool is 0.30. The probability that a home has a garage is 0.59. And since 2% have both features, we have to subtract 0.02. So this is going to end up being what for the probability that the home has a pool or a garage? 0.87. Part B says that the home has neither a pool nor a garage. Well, this one might be easier to do if we do a Venn diagram. Do y'all remember doing the Venn diagrams? Or we could do a table. I like the Venn diagrams personally, so let's go ahead and draw one. Yeah, actually we could. The question was, couldn't we just take our answer from part A and subtract it from 100? And absolutely, that would work. I'm going to go ahead and do the Venn diagram because it's easier for some people to visualize it through a picture. But yeah, we could subtract our answer from 1 because the complement of having neither a pool nor a garage is having a pool or a garage. So our pool is blue, our garage is green, and the probability of having both a pool and a garage is 0.02. What's the probability of having just a pool? 0.28. Because 30% have swimming pools. That whole blue circle represents the swimming pool. We've already included 2% right here, which means that in the whole blue circle there's going to be 30%, so that leaves 28% over here. What percentage of the homes have just a garage and no pool? Because that's this region over here, 0.57. And then add these three numbers up, and the number you get outside of the circles is our answer to part B, which we're going to add all these numbers up. We get 0.87. Subtract that from 1, and you get 0.13. I think looking at the Venn diagram makes it easier to envision that what you want to do is subtract this number from 1. So this is the pool, this is the garage, and for part B, we're looking for neither a pool nor a garage. So that's A complement and B complement. And that's going to be 1 minus 0.87, which is 0.13. Part C says you have, what's the probability you have a pool but no garage? After we drew the Venn diagram, isn't that easier to see? What is it? 0.28. Here's the group that has a pool but no garage. Would you say that having a pool and a garage are independent or dependent events? Any idea how to tell? Right now, the trouble is we don't have the formula for the conditional probability. So in order to solve that, I'm going to actually give you the formula right now for the conditional probability. The probability for A given B is equal to the probability of A intersect B divided by the probability of B. Remember I said when you find probabilities, what you do is you take the number of elements in your event divided by the number of elements in your sample space. When you have a condition here, this becomes your sample space. The condition that you're given becomes your sample space. Suppose I wanted to find the probability of having a pool given that I have a garage. So what I would do is I would find the probability of a pool given the condition that I have a garage. Using this formula, that means I would find the probability of a pool and a garage divided by the probability of what? What's my sample space? The pool or the garage? The garage is the condition that you're given. Looking at the numbers in the problem, the probability of having a pool and a garage is 0.02, whereas the probability of having a garage is 0.59. On your calculator, you'd take 0.02 and divide that by 0.59, and we get 0.03. There's a 30% chance that a home has a pool. There's only a 3% chance that a home has a pool if you know that it has a garage. So apparently it's an either-or situation in this subdivision. There's not too many houses that have both a pool and a garage. So these two things are dependent. Since the probability of having a pool is not the same as the probability of having a pool and a garage, having a pool and a garage are dependent events. In its monthly report, the local animal shelter states that it currently has 24 dogs and 18 cats available for adoption. 8 of the dogs and 6 of the cats are male. Find each of the following conditional probabilities if an animal is selected at random. Would y'all rather use a table just to see something different? We have species and we have sex. The species will be dog and cat and male and female. So we have 24 dogs, 18 cats. How many animals are in the shelter? 42. 8 of the dogs and 6 of the cats are male. So if there's a total of how many males in the shelter? 14. How many female dogs are in the shelter? 16. How many female cats are in the shelter? Get that one. For a total of 28. In this problem, we're asked to find the probability that the pet is male given that it is a cat. So we're looking for the probability of a male cat. We can do this fairly easily looking at this table. That's probability that it's a male given that it's a cat. That's going to be the number of male cats divided by the number of cats. The number of elements in your event divided by the number of elements in your sample space. How many male cats do we have? Out of, that reduces to 1/3. Part B says the pet is a cat given that it's a female. So we want to find the probability that we have a cat given that the animal is female. So now I take the number of female cats and divide it by the number of females. So how many female cats do we have divided by the number of females that we have? No, there's a total of 28 females. And 12 over 28 is, we're asked to find the probability that the pet is a cat, so there's the cat, given that it's a female. So that's why our sample space is females. No, we were told that the animal was a female. The question was, wouldn't you take into account that they were male and female dogs and cats? And the answer is no. We were given this condition that the animal was a female, so that then becomes our sample space, the number of females. We have to satisfy this given condition first. Then we look at this. So for part C, we want to find the probability that the pet is a female given that it's a dog. So how would I set up part C? We want to find the probability that the pet is a female given dog. So that's going to be the number of female dogs divided by the number of dogs. So how many female dogs do we have? And how many dogs total do we have? 24. And that reduces to 2/3. So what we're looking at here is the sex of the animal and the species. And my question now, it's not on here, but I think that I can pose it, is, does the species affect the sex or does the sex affect the species? Another way of asking that is, are sex and species independent or dependent events? Selecting the sex and the species, are those independent or dependent events? There's really one surefire way to check, and that is check and see, is the probability of randomly selecting a male going to be equal to the probability of selecting a male given that I have a particular species. What's your favorite species? Dog. Okay, good. We have dog people here. Well, first of all, out of all the animals in the shelter, what is the probability of selecting a male? The probability of selecting a male animal will be the total number of male animals in the shelter divided by the total number of animals in the shelter. So that would be the male animals. There's how many? 14 out of 42. So that would be 1/3. And the probability of selecting a male given that we have a dog is equal to the number of male dogs divided by the number of what? Dogs, because that's our sample space. So let's go back up and look at the table. How many male dogs do we have? How many male dogs do we have? 8. And how many dogs are in the shelter? And that reduces to 1/3. So are the sex and the species independent events or dependent events? Did knowing this condition change the probability of selecting a male? There's the probability of selecting a male. There's the probability of selecting a male knowing this condition. It didn't change, did it? That means that these two events are indeed independent events. Selecting the species and selecting the sex are independent events. It's a confusing concept to grasp, but it works. Treating dependent events as independent. Even if events are dependent, sometimes we can treat them as independent just because we have a whole lot of things and the difference that it's going to make in the probability is insignificant. Some calculations are cumbersome, but they can be made manageable by using the common practice of treating events as independent when small samples are drawn from large populations. This book uses the 5% guideline for its rule of thumb for cumbersome calculations, meaning if your sample is less than 5% of the population, you can assume independence. Remember the good batteries and the bad batteries we talked about? Those were small samples. 5 out of 12 were bad, 7 out of 12 were good. We had a very small sample. But let's say that I'm doing quality control at a plant, and we're producing widgets, and we produce 100,000 widgets a day, and I want to select 10 an hour just to sample. During an 8-hour shift, that means I've selected a total of 80 widgets. Well, 80 out of 100,000 is very, very small. So there I can assume that my 80 widgets are and independent is good because when things are independent, it makes calculating probabilities easier, because then the probability of an event given that something else has already happened is just going to be the probability of that event. So for example, suppose 50 drug test results are given from people who use drugs. There were 44 positive test results, 6 negative test results. Now these are people that we know use drugs, so that's a total of 50. So 2 out of the 50 subjects are randomly selected without replacement. That's only 4% of the population of 50. So find the probability that the first person tested positive and the second person tested negative. We've got two things happening here. The first person tested positive, the second person tested negative. Testing positive, we could say there's a 44 out of 50. The probability of getting a positive is 44 out of 50, or 88%. The probability of testing negative is 6 out of 50, or 12%. The first person's positive, that's going to be 0.88 times 0.12. And what is 0.88 times 0.12? It's 0.0156, so we'll call that 0.11. 0.11. Actually, how many places do we round to? We need to go to 3 decimal places, so we'll call that 0.106. We go to 1 place more than our probabilities here. Where did I get the 15? It's not 15, it's 50. So we can assume that that probability right here is going to remain constant simply because we're looking at a small sample size. So let's look at another problem. It says when 2 different people are randomly selected from those in your class, find the indicated probability by assuming birthdays occur on the same day of the week with equal frequencies. So we want to find the probability that 2 people are born on the same day of the week. So we have our first person. They're born on a day. Second person's born on the same day. Did we specify how many days, what day that first person had to be born on? No. So we have a total of 7 choices out of 7 days of the week there, don't we? The second person, though, has to be born on the same day. So now there's only 1 choice out of 7 days of the week. So the probability here would be equal to 1/7. This is for part A. For part B now, we're told that 2 people both have to be born on a Monday. So the first person's born on a Monday, the second person's born on a Monday. That means now we only have 1 choice out of 7 days. Are the days of the week that people are born on independent or dependent? Independent. When I was born doesn't depend on when you were born. This person has a 1 out of 7 chance of being born on that same day of the week. So this is going to be equal to what? 1 out of 40. Another way for counting things is by using a tree diagram. A tree diagram can come in handy. I believe you may have seen these before. This is a way that we can use to calculate the total combination of things. This figure summarizes the possible outcomes for a true-false question, and then followed by a 5-choice multiple-choice question. So we have 2 questions times 5 questions, or 2 choices times 5 choices gives us a total of 10 choices for answer combinations on a 2-question quiz. The probability of guessing and getting both answers correct, or making 100 on the quiz, then would be the number of ways that we could get the answers correct divided by the number of elements in our sample space. Well, there's only one way to get both questions correct, and that's for the first question to be correct and the second question to be correct. So there's 1 choice there, but there's a total of 10 possible choices for our answers here, so that would be 1/10. The probability of guessing, making 100, would be 1 out of 10. So looking at some fundamentals of counting, it says in the addition rule, the word or means probability of A or B. That suggests addition. Or goes with addition. And, as long as the events are independent, is going to be multiplication. So multiplication, the and here means we're going to be multiplying, but you've got to be careful that the events are either independent or the probability of the second event is adjusted so that we take into account what happened first.